So with this information, if we go back to our Mars probe that had y of t equals 120,000 minus 1.17 t cubed, that's our altitude, right? Then, things we can say are that y prime of t, we can just very instantly say, what's 1 times 1.7? It's negative 3.51 t squared. That is velocity. And so we can say specifically that y prime of 25 is negative 3.51 times 25 squared, and that equals negative 2187.5 meters per second, and that is the velocity at t equals 25 seconds. All right, we could say more very easily now. We can say what the acceleration of that Mars probe was. So we can say that that is, so we can just use our power rule again, right? 2 times negative 3.51, so it's going to be negative 7.02 t. That's the acceleration function. And then that's y double prime of t, which is the acceleration. So y double prime of 25 is negative 7.02 times 25, and that is negative 175.5. Now the units on this will be meters per second squared because it's an acceleration. We can call this v of t, we can call this v of 25, we can call this a of t, we can call this a of 25, and those are all different ways to express velocity and acceleration at any time t and at a specific time t. All right, so what else do I want to say about that? Yeah, all right, so you want to say like generally about units, since we're talking about the meters per second squared here. So now let's go back to that the f of t could represent anything, not just position, and it's measured in, I'm not going to use equals, I'm just going to say it has a certain units, okay? So for example, in heat energy, it might be joules, or in temperature, it might be degrees centigrade or degrees Kelvin, or if we're measuring population, it might be number of people, okay? Then f prime of t is going to be units per unit of time. So for example, degrees centigrade per hour, or joules, kilojoules per year, something like that. Units per time, meters per second. And then f double prime is always going to represent some kind of acceleration. So you think population, for example, has an acceleration as well, so we can talk about population is going up, we can talk about how fast is it going up, and we can say how fast it's going up, changing. Right, that's what we mean by acceleration. What's the acceleration of population? Or, what's the acceleration of infection of a virus? Something like that. All right, so that f double prime is always going to be in units per time squared, right? So it's going to be degrees centigrade per hour squared, or meters per second squared, or people per year squared, right? So that's how we measure those things. So specifically for position, if y of t is in meters, then y prime of t is going to be in meters per second, and y double prime of t is going to be in meters per second squared, all right? So a natural question for people to ask at this point is, y double prime is also a function, right? So when we got our acceleration function, right, so, keep your eye on the fact that all of these things are functions. All right, so position is a function depending on t, velocity is a function depending on t, acceleration is a function depending on t. I can do the derivative of a function. I could do the derivative of this function. Would it make sense for me to look at y triple prime of t? Indeed it would. Now, your book calls this quantity jerk. All right, so think like we're accelerating, but then your acceleration's accelerating, so it's like you're jerking something, okay? That's where that comes from. I never heard this word used for the third derivative until I came to Danbury 10 years ago and started using this book. And there was the word jerk. I forget which page it's on. I'm not going to go look for it. But it's the first time I ever saw it. But then I talked to some people, and some people in engineering say, oh yeah, we use jerk. It's the third derivative. I had never heard of it before. Now you know, and it's meters per second cubed. And so now you can be a snarky mathematics guy and say, you're such an x triple prime. You're such a third derivative. Yeah. All right. So we can keep going for the Mars probe, right? So we have y double prime is negative 7.02. Then y triple prime, which would be our jerk, would be, just since we have negative 7.02 t, y triple prime would be negative 7.02. And then what would we call the fourth derivative? We don't call it y with 4 marks because we're just going to have marks going forever. So what we do is we start using Roman numerals, right? This is like a Roman numeral 3, Roman numeral 4. So we say the fourth derivative of t is what? It's 0. And then we can keep going. The fifth derivative of t is 0. They're all 0 after that, okay? So we can start to talk now. These are called higher order derivatives. So after the first derivative, the second derivative and higher are higher order derivatives. That is the next thing that we're going to talk about.